So the key to really understanding mechanism is to recognize patterns of mechanism. And so as we've discussed in class, there are really 4 of these that we see over and over again. And so I want to take a second shot at helping you to master this information and immediately apply it to the 2 mechanisms that we discussed on Wednesday, and also apply it to some of the mechanisms that we need to learn on Monday. My hope is that this will help reduce the intimidation factor a bit and will allow us to really absorb a lot of this material in class on Monday. So the first important mechanistic pattern that we see is the proton transfer. And of course, by proton, we're talking about a hydrogen ion. Even more specifically, we're just going to be removing, or moving rather, an H from one molecule to another molecule. So let's look at a couple of the more frequent examples. Of course, we know that if we have an acid-base reaction, for example, if we have 2-butanone and 2-butanone is reacted with a molecule of HBr. Remember, HBr is already polarized because the bromine, being more electronegative, has a partial negative charge, and hydrogen, having a less electronegativity, has a partial positive charge. This can best be remembered through the simple mnemonic Fonkelbrish. And if you're not down with that, Fonkel you brish. This gives us the descending order of electronegativity for the first 9 elements on the periodic table. So fluorine is the most electronegative atom that makes a bond, then oxygen, then nitrogen, then chlorine, then bromine, then iodine, then sulfur, then carbon, then hydrogen. So you have an HBr bond. Bromine has a greater electronegativity and it will polarize this bond or weaken this bond. And so in a proton transfer step, 2 of the lone pairs of the carbonyl oxygen, of course that's our best nucleophile, and the partial positive charge of the hydrogen atom, that's our most reactive electrophile. Again, tail of the arrow is where the electrons originate. Tip of the arrow tells us how many electrons are moving. In this case there are 2 because it is a double-headed arrow. We are going to point that arrow directly to the atom which has the partially deficient in electron density orbital and will receive this nucleophilic attack. And of course hydrogen is monovalent, therefore as the OH bond begins to make, the HBr bond begins to break. Now if we start thinking about transition states, and transition states were something that we discussed last week or week before last, it's important that we realize that this process happens nearly simultaneously. And so as I'm beginning to make this OH bond, I'm beginning to break this HBr bond. And of course, the bromine has a partial negative charge, while the oxygen has a partial positive charge. So we typically will bracket this on our potential energy diagram, and we'll give it a superscript transition state. Both of these, the arrow pushing and the transition state, give us an idea of how this molecular movie is progressing. The more specific, of course, is the transition state. But commonly, we're going to use this arrow pushing. So both of these are fair game. You want to know both of them. Now let's think about the product after this reaction is completed. The carbonyl oxygen will now be participating in 3 chemical bonds with a lone pair and an integer positive charge. This is significant because the positively charged oxygen is going to create a significant dipole difference. And so now this carbon that I'm highlighting, actually I'm going to highlight this in pink, is much more electrophilic than it was before the acid-base reaction. Also, I have produced bromide ion. And just looking ahead to the next step, the bromide ion will be my most reactive nucleophile. The carbonyl carbon will be my most reactive electrophile. So as you might expect, one possible mechanistic step is the attack of bromide and one of its lone pairs on the carbonyl carbon, and then of course the carbon oxygen pi bond will break. So this is one example of a proton transfer. Let's take a look at one that's a little different. And this will make more sense once we get to elimination reactions. We're not quite there yet. But Klein certainly shows this example in chapter 6, and it's certainly something we're going to be dealing with in the future. So we have a carbocation intermediate. We've already seen a couple of things that can happen. One is nucleophilic attack. So let's imagine we have a Br minus that is a really good nucleophile, but a really unreactive base. And of course, it just overlaps with one of the empty lobes of the p orbital in this carbocation. That is certainly possible. This is a separate pattern, one I want to talk about in a few minutes, but this is nucleophilic attack. And of course, I've made a carbon-bromine bond. There's another possibility. Let's say we have a weak nucleophile, but a strong base. Typically something that is a weak nucleophile and a strong base will be a very large, bulky polyatomic system like tert-butyl oxide, T-butoxide. And the bulk of all these methyl groups are going to prevent any kind of nucleophilic attack, but it very readily acts as a base, removing a proton and alleviating the carbocation by forming a carbon-carbon double bond. So our product would be propene and of course T-butanol would be a byproduct. This is also a proton transfer. Proton transfers are always going to be performed to 1, activate an electrophile, 2, to generate an intermediate, like a carbocation intermediate, or 3, to alleviate an intermediate, like a carbocation intermediate. So these proton transfer steps are ones you always want to look for in a particular reaction mechanism. Let's take a look at an application of this. I'm actually going to use a different color scheme this time. Let's imagine that we have this starting material. Of course, if we're naming this, we are going to have 3,3-dimethyl butene. Don't have to name it as a 1-butene because the carbon-carbon double bond, by virtue of the name, is assumed to be between carbons 1 and 2. Let's imagine that we are going to react 3,3-dimethylbutene with a molecule of HCl. So of course, if we have HCl in solution, we also have H2O in solution. So there's going to be a competition for some acid-base chemistry. HCl is obviously going to win. Best electrophile will be this deficient hydrogen bonded to HCl. Best nucleophile, remember we see this pattern over and over again, the pi electron density in the alkene. And so our arrow pushing, tail of the arrow where the electrons that are nucleophilic originate, tip of the arrow, if it's double-headed, there's 2 electrons that move, there are 2 pi electrons, and of course tip of the arrow pointing to the atom whose partially electron deficient orbitals overlap takes place, and of course the HCl bond must break because hydrogen is not divalent. Cl- is a product of this reaction, and also we generate a carbocation intermediate. This step is best described as a proton transfer. This is a proton transfer step. Now let's go to the next step in the mechanism while I already have this one up to illustrate a second pattern that we see in mechanism. And that, of course, is one of a rearrangement. Anytime you have a secondary carbocation, the simple question needs to be asked, is there a hydride shift between carbons 1 and 2, or carbons 2 and 3? Important point is they must be adjacent. That can take its electrons and rearrange and make a more stable carbocation. Well, you have 3 hydrogens attached to this terminal methyl group, but none of those hydrogens will rearrange because you would convert a secondary carbocation to a primary. We can also have a 1,2 alkyl group shift. And so one of these methyl groups with its electrons will move, in this case, from carbon number 3 to carbon number 2. This scrambles the carbon skeleton. It's now more highly branched than it was before, And notice I have a more stable carbocation intermediate. Of course, we term this mechanistic step as a rearrangement. I don't want to leave you with the impression that the only types of rearrangements that occur are 1-2 shifts. However, in your course, at your level, this is the only one you need to worry about existing. So a rearrangement can and will take place to produce a more stable carbocation intermediate. Let's take just a moment and look at the potential energy diagram of such a process. So I'm going to draw free energy, G, as a function of reaction progress. Pay careful attention to how we do this process, because in all likelihood you will have to do this on your take-home examination in some form or fashion. So we have the initial energy of our reactants. Of course, our initial reactants are the alkene that is unsymmetrical and HCl and H2O. Now, there is an activation energy barrier, an intermediate, smaller barrier, a lower energy intermediate. That's what we know thus far. In this first energy of activation step, we want to show that we are breaking our pi bond and we're beginning to make a carbon-hydrogen bond, and we're beginning to break a hydrogen-chlorine bond. So this transition state represents this position on our energy hill. Of course, our first intermediate is the secondary carbocation that we form. Of course, the second transition state is going to correspond to this 1,2 methyl shift. And so I'm actually going to draw the methyl group. And this is intended to show that the methyl group is going from carbon number 3 to carbon number 2. And of course, we have a partial positive charge here, and we have a partial positive charge here. Second intermediate will be the more stable carbocation. And finally, we'll have a third transition state and then our product. Our third transition state is going to show the bond that is beginning to be made between our best nucleophile. In this case, I'm just going to show you the possibility of Cl- attacking. Partial negative charge, partial positive charge. And of course, in products, we've already made the bond. The difference in these two energy states is our delta G of reaction. Notice this represents an exergonic reaction. Of course, we have different energy of activations. This, of course, is the slow step, generating the first carbocation intermediate. This is the second step. And of course, this is the third step. So this really shows us all of the detail in this mechanism that one would need to see. Let's label the mechanistic patterns. In step 1, we have a proton transfer. Step 2, we have a rearrangement. Step 3, we have nucleophilic attack. So 3 of the 4 patterns are represented in this electrophilic addition reaction, which makes electrophilic addition a great model to begin to master these different types of mechanistic patterns. Now we could show this a slightly different way if we look at a reaction called nucleophilic acyl addition. So we will generate a nucleophile from an electrophile. So the first step of this mechanism is simply going to be the same kind of proton transfers that we're used to seeing. And what I'm going to attempt to do now is animate electron movement. So I'm going to highlight the nucleophile, and the nucleophile is going to begin to approach and make a bond with the electrophile. And so the oxygen is going to begin to assume a partial positive charge, while the forming bromide will begin to assume a partial negative charge. And of course, after this first step of the reaction is complete, notice we have a conjugate acid and a conjugate base. These are 2 other hallmarks of a proton transfer reaction. And what we've really accomplished is we're now activating this carbonyl carbon for nucleophilic attack from a nucleophile like H2O. And so in class on Monday, we will learn about how we make a hydrate, where we convert an aldehyde or a ketone into a geminal diol. Let's take a look for a moment at how that might work mechanistically. So let's choose 2-pentanone and HBr as our acid catalyst. Remember, we also have water in solution. And so our best electrophile will be the partially positively charged hydrogen in HBr, while the most reactive nucleophile will be one of these lone pairs associated with the carbonyl oxygen atom. Most reactive nucleophile makes a bond with the most reactive electrophile. Of course, we need to show all of our lone pairs. It's really important when you do a mechanism that you show all relevant lone pairs. And so when this step is concluded, I now have an activated carbonyl carbon as a result of protonating an oxygen atom and Of course, by induction, we're going to withdraw a significant amount of electron density from this bond. Now we also have Br minus that's left in solution. And we have H2O that is left in solution. So the real question now is, which of these two is the better nucleophile? A lot of you will be tempted to say that it's Br minus because it has a negative charge. And that is not bad logic. However, HBr is a stronger acid than H3O plus. So the conjugate base of the weaker acid is going to, in this case, be the better nucleophile. That means it is H2O. This mechanistic step is nucleophilic attack. We can have attack from the front or from the back. The pi bond, of course, will break. And we will make what we call a tetrahedral intermediate. And what we mean by this is that the geometry of what used to be the carbonyl carbon has gone from trigonal planar to tetrahedral. And the final product is going to be realized when Br minus deprotonates what used to be the water molecule to yield two neutral products. The geminal diol, by geminal we mean that both OHs are on the same carbon. We call this a gem diol, as opposed to a Vic diol, which means they're on adjacent carbons. So mechanistic steps. We have a proton transfer. Clearly we are transferring a proton from one molecule to another. In our second step, we have nucleophilic attack. And in our third step, we have yet another proton transfer. So 2/3 of our steps are proton transfers in this mechanism. Let's talk at a bit more length now about nucleophilic attack. And I've already shown you a couple of practical examples. I'd like to continue at just a bit. So as an example, let's look at nucleophilic acyl addition. If I have a strong nucleophile, this can occur without activating the carbonyl carbon. So if my nucleophile is CH3 minus or NH2 minus, this can occur without having to use an acid catalyst. Best nucleophile attacks the most reactive electrophile. And now I've made a new carbon, just to show you the transition state, a new carbon nucleophile bond. And it's, again, tetrahedral. Nucleophilic attack can take a lot of different forms. And when we explore Chapter 7, which we'll be doing in 2 weeks, you need to note the difference between the sequence of events that can occur when you do a substitution reaction. When you do a substitution reaction, there will be nucleophilic attack. So y'all take note of this because it will come into play later. You will have nucleophilic attack and you will have loss of a leaving group. They can both occur simultaneously. And again, I mentioned this on Wednesday. I'm going to say it again. We call this an SN2 mechanism. We could have loss of a leaving group first, then nucleophilic attack second. We call this an SN1 mechanism. Or we could have nucleophilic attack first and then loss of a leaving group second. We call this nucleophilic substitution. We don't actually cover nucleophilic substitution in first semester orgo, but it is covered in depth in second semester orgo. This is nucleophilic acyl addition. And so we are adding across a pi bond. Just like before, we added across a carbon-carbon double bond. And the two reactions we've discussed to date in detail have been adding water across a double bond. We call that hydration. And adding the elements of HBr or HCl across a double bond. We call that hydrohalogenation. So I've already shown you the hydrohalogenation mechanism for a second time. Let's now look at the hydration mechanism. And I'm going to use a simple example, just like before. My reagents are going to include an acid catalyst. I'm going to use HCl and H2O. Of course, even when HCl is at its most concentrated, it is only 37% HCl and 63% water. So if we do the arrow pushing, as you might expect, you are going to see a proton transfer step to get the reaction started. So proton transfer, just like we've seen. This is going to generate an initial secondary carbocation intermediate. We can have a rearrangement. In this case, it's a 1,2 methyl shift. And of course, this is going to produce a tertiary carbocation intermediate. Now there's a competition between the nucleophiles H2O and Cl-. H2O wins this battle. It's the better nucleophile because it's the stronger base. So in this third step, we get nucleophilic attack. Okay, so let's keep track of our steps. Step 1 is a proton transfer. Step 2 is a intramolecular rearrangement. Step 3 is nucleophilic attack. After nucleophilic attack is complete, we still have one last step to generate our alcohol. And of course, this last step will be a final proton transfer. So we're going to justify the reformation of HCl. This does not actually happen this way in solution, but this is perfectly acceptable on an undergraduate mechanism. Just quickly, what happens in solution is we have HCl. HCl has a pKa of -7. Remember, there's a number of pKa's that you are responsible for learning. And if our other reactant is water, where water is the base, must be getting late because I am losing my drawing touch. we will produce Cl minus, and we will produce hydronium. The pKa of hydronium is -1. That means that the equilibrium constant of this reaction is about 1 million. This essentially is irreversible. All of my HCl will dissociate, and hydronium will actually be the identity of the acid catalyst. Again, this is what really happens in the solution. You are responsible for showing the mechanism, and if you choose to use HCl, if that's simpler, then go ahead and use HCl. So the only mechanism pattern we've yet to talk about in this screencast is the loss of a leaving group. And so I want to foreshadow SN1 mechanisms. And so let's imagine that we have 2-bromo, 2-methylbutane. And we want to make the corresponding alcohol. And so we have hydroxide ion in solution. This mechanism is going to proceed by a 2-step process. Step 1 will be the loss of a leaving group. It does this only in the presence of a nucleophile. And so this bond is going to break, and we will create a nicely stabilized tertiary carbocation. Now, let's take a minute to talk about this carbocation. The carbon is sp2 hybridized, which means we have a methyl group, we have another methyl group, and we have an ethyl group. Now, I can't really draw this in the plane of the screen, but you're going to have a P lobe that peels out of the plane of the screen coming directly towards you, and one that goes into the plane of the screen directly away from you. And OH minus can attack either one. Now remember, the leaving group is going to, when it leaves, it's going to come out of the plane of the screen towards you. So it's going to block, if you will, some of the hydroxide attack from the front. In your textbook, you're going to read that you get equal distribution of these two isomers, but that isn't quite true. You get a little bit more from this backside attack of the nucleophile, which is going to cause the OH bond to be made in the plane of the screen. So when you get this backside attack, you want to show this as a dash. And when you get some of this front side attack, you want to show the COH as a wedge. We'll talk a whole lot more about this on Wednesday when we talk about stereochemistry. There is an off chance that we are going to get into some of this on Monday. A lot of that just depends on how well you all handle this information. It's my hope that we can begin to handle some things better than what we've done. And so this is, number 1, loss of a leaving group. Number 2, nucleophilic attack. So in short, these are the mechanistic steps you need to know. Proton transfer. Look for a hydrogen being swapped from one atom to another. Rearrangement. Look for the formation of a more stable carbocation. Nucleophilic attack. Look for the formation of a heteroatom or other type of atom carbon bond. And of course, loss of a leaving group, generating a carbocation intermediate. Study these well, and if we do, I will make you this promise: the information should flow more easily on Monday. So I will do my best to take my time as we go through this material. I know it is intimidating. It was intimidating for me when I learned it. And so, I mean, I realize this on the front end. We just really need to be really productive during our class time. And so I also want to set aside some time to work on some problems that help you master this. Remember, I will be posting the take-home exam on Wednesday, and it will be due, I'm going to give you a week to do it, so it will be due the following Wednesday. I know I previously said Monday. I've changed my mind on that, so I'm assuming no one has an issue with me extending the deadline. And I will see you guys in class on Monday.